Should I turn?
It's fine.
But yeah, apparently I owe you guys another quiz since I only gave you 20 points for this one. I'll try to give you another quiz sometime soon. It seems like I need to make the next quiz also worth 20 points.
I mean, yeah.
Because somehow while I tried to give you a gift, some of you were unwilling to take it. So, all right, so find my notes here. So today we're going to talk about the concept of a generating set. So if we have W is equal to the span of S, all right, and this is all inside some vector space V, all right, then this set S is called a generating set. Right? So if you have a span, if you have a subspace, right, if you can find a set for which the subspace is formed by the span of that set, then such a set is called a generating set. The generating set's not unique. There's a silly theorem in my notes. For example, you can have span of S equals to the span of T. I prove span of S is equal to span of T if and only if each vector in S is a linear combination of vectors in T and vice versa. So that theorem alone I'll watch Belu. So this theorem alone shows you that the spanning set is far from unique. All right? Far from unique, this generating set. Because you can form so many different possible linear combinations right, from a given set of vectors. That's a theorem that's in the notes, which is true. Rather than saying too much more about that, I just want to show you an example. So here's an example. I'm going to go over here. Find a generating set for, let's say, W equals to, let's say, x, y, z, such that x plus y plus z equals to 0, and y plus z equals to 0. All right? In other words, I want to find some vectors, or a vector, whose span gives me back this set. So how do you do that? Let's see here. I guess what I would do is I would let A equal to 1, 1, 1, 0, 1, 1, all right? And notice that x, y, z is in W if and only if x, y, z is in the null space of A. The null space of this matrix is W. I have a 3-vector times that matrix B0 is to say those two equations. Okay, so then what? Well, usually the reduced row echelon form of the matrix has something to tell us, right? Reduced row echelon form of A we can get from just one step, right? Just subtract the second row from the first row, you get 1, 0, 0, 0, 1, 1. There you go. That's the reduced row echelon form of A. just one step. There it is. Let's see here. What else can I say? So that tells me that if x, y, z is in the null space of A, then, well, we've got two things, right? We've got x equals to 0, and we've also got that y plus z is equal to 0. So we could write that a little bit more. So that's what? X, y, z is in fact equal to what? It's equal to 0. And so usually I take this equation and I use the pivot as a dependent variable. So here y is equal to minus z, right? This calculation we're doing right now, it should be a little bit familiar. This is essentially one of the questions I asked on the test. Okay, so I'm going to use y as a dependent variable, z as the parameter, essentially. So I get minus z comma z. So if you look at that, you can factor out the z, and you got what? 0, minus 1, 1. Therefore, the null space of A is the span of 0, minus 1, 1. There you go. The generating set here is kind of a boring set. It's a set containing one vector. It's just a singleton, right? Is the choice unique? Not really. I mean, you can take any linear combination. I mean, any scalar multiple of that and still have another. I mean, here's another thing you can do that would be kind of stupid. You can say this is the same as the span. It's not too interesting, but here's another thing you can do. Right, I could add another vector and it wouldn't change the span, right? I'm just adding more copies of what I already have. Think about it, it wouldn't change anything. Yeah?
Wouldn't it be negative 2, 2, as opposed to 2, negative 2?
Doesn't matter.
You multiply by negative 2.
I see.
There's another theorem I should probably mention here. Theorem. If I have span of say v1, v2, vk, then that's equal to the span of v1, v2, vk, and adjoin any arbitrary linear combination of set vectors. So if I add a linear combination of things that's already in the span, it doesn't change the span. We essentially discovered the reason for that in one of the previous classes we just had, where we proved that a linear combination of a linear combination was, yet again, a linear combination. And that suffices to prove this claim. Let me do another example for you, which is perhaps a little more interesting.
Oh. So I'm right on that one?
Sure. Let's find generating set for w equal to f of x in, say, third order polynomials, such that f prime of 0 is equal to 0, and f of 1 is equal to 0. So I know that third order polynomials possibly degenerate forms a subspace of the set of all polynomials, which itself is a subspace of the set of all functions from R to R, if you think of polynomials as functions. So this is a reasonable question to ask, right? There's a context in which it has, sitting inside a larger space, which is also a vector space, where the operation of vector addition is just function addition, right? So we can kind of know, we know where we are. I can't say words. Okay, so the way to discover what the spanning set is to actually look at a generic element. All right, so the last example was a little bit special because it concerns column vectors. And there we have special tools which we can bring to bear from the first part of the course. This problem, on the other hand, we kind of have to start from scratch. So we start with a generic element, f of x is equal to ax cubed. plus bx squared plus cx plus d. That's a generic, non-specific element in P3. That's what a generic, that's what it looks like, right? Now, to say f of 1 is equal to 0, what's that mean?
ax cubed plus bx squared plus cx plus d equals 0.
Right.
Or a plus b plus c plus d equals 0.
Okay, a plus b plus c plus d.
Since x is 1.
Right. That is true. That's a condition we have on a, b, c, and d. What is it to say f prime of 0 is 0? So that's 3ax squared plus 2bx plus c, all parentheses, evaluated at x equals to 0, which would be what?
C equals 0.
Yeah, c is equal to 0. So I don't think we really need matrix techniques to unravel this system, right? We can just kind of go, okay, well, this equation is easy enough to understand, z equals to 0. So you take that and you put it in the one above, and what do you get? You get a plus b plus d equals to 0. And you got choices here, right? You could use, apparently we're going to have two parameters. I'm going to let a be the dependent variable. A is equal to minus b minus b. So apparently my generic, my generic polynomial, it only depends on actually two parameters when the dust settles. Let's write it out. And f of x equals to minus b minus d, parentheses, times x cubed, plus bx squared. C was 0, right? C is 0, so there's no x term. And then plus d. Now, in order to discover what the generating set is, to view this subspace as a span, I have to see a generic element as a linear combination of two specific, one or two or three specific vectors in the space, right? So what you do is you do what I'm doing, and then just basically pick your parameters. Here the parameters are d and d. Try to pull them out and just see what's left. And whatever sits beside the parameters will be the vectors which form the span. So here I've got b times minus x cubed plus x squared plus d times minus x cubed plus 1. So obviously f of x is a linear combination of, this vector here and this vector, right? So therefore w is the span. This calculation makes it clear that w is the span of minus x cubed plus x squared and minus x cubed plus 1. Again, I could do something silly. I could just add, I could add something else. Basically, I could do, I could also do minus x cubed plus x squared minus x plus 1 minus x cubed plus 1, comma. I could just, take any combination of these if I want. For example, the difference of them. I could have x squared minus 1. That wouldn't change the span. Take any linear combination of the first two, you won't change the span. So what's the difference, all right? I've been messing up our generating sets in some sense by just adding another vector at the end of the example, right? It's kind of an ad hoc thing to do, right? Like, wouldn't it be desirable to be able to know what's the minimal spanning set? Like, so, the generating set, think about it. Why make do with two things when you can make do with one? Or over here, why have three things to form the span when you can have two, right? It's an important problem to be able to find the smallest number of vectors possible to make up the span.
So why don't you just add the other one?
To show you that it's not unique, that you could have more than you need. Just because you find that something's a span doesn't mean.
If it's just a linear, or if it's just a scalar of another one of the vectors, what's the point? Well, writing that out.
Right, so what's the difference between the set before and after I messed it up by adding a linear combination? Well,
It's a linear combination of the other vectors. So basically, the vector lies in the same plane as the or span of.
Thinking geometrically, okay.
Sorry, I'm just okay. It lies in the same span.
I'm not disagreeing with you.
Ah. Okay, whatever.
I broke Christian's brain, no. Although I will point out that you just talked about a plane in the same plane.
Well, I mean,
But-
it's not the same context. That's why I changed it to span.
I don't disagree with you. Maybe it does make sense to talk about a plane of polynomials. But you should understand you're saying that in somewhat abstract context, right? Like, 'cause these are polynomials or not. I'm not disagreeing with you, I think so. So there's a distinction between this set, let's call it S, and this set here, let's call it S prime. Like you just told me, this one has a linear dependence amongst the vectors, right? So the second vector, this subset right here, ignoring the span, okay? I'm not talking about span. So just the set, the generating set here, this is linearly dependent. It's a linearly dependent set of vectors, right? Linearly dependent. S, on the other hand, is linearly independent. Over here, this guy, if you just have a set containing one non-zero vector, guess what? It's linearly independent, but this set over here was linearly dependent.
So we're supposed to remove enough vectors that it's still the same span, but it's linearly independent.
That's exactly the point. The minimal spanning set will be the generating set, which is also linearly independent. So this is how
you're
linear.
doing this approval point.
Yes.
Okay.
So the linear independence. I'm trying to teach, but
Yeah,
the linear independence. Linear independence is an important criteria for a set, right? It tells you whether or not you can get rid of something, right? Because if it's a linearly dependent set, that means one of the vectors, at least one of the vectors, is a linear combination of the others, right? But you can remove that kind of vector and not change the span. Right? Okay, so, for the purists in here, or those who have been paying really close attention, are sufficiently legalistic, I don't know, whatever kind of criteria you want to put on yourself. You might have noticed I never defined linear independence in a vector space, right? I defined linear independence in Rn, which is different, right? However, good news, linear independence in a vector space is defined in exactly the same way. So, let me give you a list of equivalent conditions for this Barker struggles on. Has not long to live, but it brought us this statement. Okay. So number one, oh, and I should give this stupid set a name so I don't have to keep writing that S. Okay, I'm going to call S the set. S is linearly independent. So our fundamental definition meaning there does not exist a linear dependence amongst the vectors in S. And I should be clarifying, I mean a non-trivial linear dependence, obviously, yeah.
What's the symbol next to the V?
This one? That was
No,
just,
the other one. The other one.
oh, that was just an
To
arrow.
the left.
Subset.
Subset. Okay.
Right.
Thank you.
Sure it was.
You can't be subspace. Subspace has infinitely many things, always.
Isn't that the more
Over the
angular?
reals. Not over the pipes. Yes?
Isn't that the subspace one? Isn't that the angle one?
Yeah, subspace is like less than or equals to, like, let's say. So, anyway. Number two, you should recognize this one as, well, if C1V1 plus da 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 plus CKVK equals to 0 implies what? C1 equals to 0, all the way on to CK equals to 0. So the only linear combination which produces the 0 vector is the trivial combination. It's another way you can characterize linear independence of k vectors in a vector space. The proof that 1 and 2 are equivalent is the same as the proof I showed you in Rn, so I won't repeat it here. 3, and we use this all the time in calculus. You guys didn't maybe realize this, but there are places in Calc 2 where we equate coefficients of things, right? What we're doing there is we're using the linear independence of those things, actually. So here's how that goes. If C1 V1 plus da 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 C K VK equals to B1 V1 plus da 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 plus BK VK, if this implies that C1 is equal to B1, and so forth and so on, CK is equal to BK. That's another way. If your set of vectors has the equating coefficients property, right? If your set of vectors has the equating coefficients property, that serves to characterize it as linearly independent. So this altogether is the equating coefficients property. Yes, Dr. Professor Landon.
Dr. Professor Cook, so this is basically why we're allowed to add like 2x and 3x and 4x squared and 5x squared, not like 4x squared and 3x? Or maybe not, I don't know.
You can add polynomials. This is why.
What is this saying?
What is it saying? This is saying that it's
Like you said,
completely unambiguous. If I have 3x squared plus 2x plus 3 equals to ax squared plus bx plus c, for example, that implies that 3 is equal to a, 2 is equal to b, and 3 is equal to c, right?
Yes.
In other words, polynomials, more specifically the set of monomials, s equals to, say, x squared, x, and 1. There's a set of monomials. This is a linearly independent set of polynomials, in particular monomials, because it has the equating coefficients property. Or you could argue that way, because this set is linearly independent, it has the equating coefficients property, if you believe this list of equivalences that I'm telling you. Yeah.
So, but that's like, x squared and like x, like those two things are linear. But if you say you have the s equals x squared and 2x squared, x, well, that would not be linearly independent.
Oh, yeah. For a counterexample, if I had, very good point, if I had 2x squared plus x squared is equal to 3x squared plus ax, x squared, I could not then, oh, sorry, 2x squared. Well, maybe 2x squared I could. Let's see here. Oh, how about a and b? And I'll put a 2 here to make your point. Yeah, it would then not follow that a is equal to 2 and b is equal to 1, right? I mean, a equals 2 and, a equals 1 and b equals 1 are one solution, but there are many, many others. What is it, Ms. Bailey?
I think I get accept.
Oh, you got accepted somewhere.
Yeah.
Yay.
Where?
I couldn't tell if it was that Michael got accepted somewhere else again, or...
SMU.
Let us not discuss this as it will go onto the internet, where so many people are paying attention to this marvelous.
I'm sorry.
How many?
Did you send in your scores?
What?
You actually
Did you send in your scores?
Yeah.
I have 30 views? Wow. I gotta start monetizing this channel.
You're gonna replace open courseware.
Replace it.
You just like teach online and like,
Just teach online? Hmm.
No, like not just teach, or like just like do an online like series.
Like the gap in content.
Oh, I'm gonna go on. So,
You retire after this.
Sorry. So, but this is actually Dr. Christopher Landon's question is actually very good. If I try to equate coefficients in a set which has linear dependence in it, it's not, there's an ambiguity, right? I could either go a equals 1, b equals 1, like that. That would be a solution, right? But I could also do, this is actually just, what, 3x squared, right? So I could also choose a equals to 0 and b equals to 3, right? In fact, there are infinitely many different ways you can form a times 2x squared plus bx squared to match this 2x squared plus x squared. because x squared and 2x squared are not linearly independent. So those are the three big ones. Now, first, there's a couple of small, like little, well-known facts that we should know and we should have at our disposal about linear independence of sets. Let me get those. Let me get those on the agenda here. Well, that's a mess. First of all, if you got 0, if 0 is in your set, guess what? That is not linearly independent, right? It just takes one rotten apple to spoil the bunch, and 0 is that rotten apple. I mean, 0, if there's 0 in the set, it is not linearly independent. Okay, so I'm not sure this is a theorem. This is kind of a little tiny theorem. So if 0 is an element of S, that implies that S is not linearly independent. Which is kind of a funny way to talk, because I'm now saying that S is not linearly dependent. But, sorry, that's punk talk. Proof. Okay, so like 0, 1 times the 0 vector is equal to 0, yet, well, that's it. I mean, that's it. Because that violates 2. This contradicts item 2. It doesn't matter if 0 is the only vector in there either. So, another theorem. If you have a set, say V and W, then VW is linearly independent if and only if, what I mean to say here is let VW subset some vector space V, right? Then VW is linearly independent if and only if there does not exist K in the reals such that, say, V is equal to K times W. Okay, you can prove this. Well, let you guys think about the proof of that, and you can. Somebody figures out the proof of that, they can put the proof on the board here before class next time. Okay, that's what you guys have to do.
Vector proof?
Yep.
I said extra
You
credit.
said yes, it's a thing.
Extra credit.
He said yes?
If he hadn't asked about it,
He already
he
said
would've-
yes, he already
No,
said yes.
you said for extra credit, and you went, yes.
So you already said yes for extra
And it's on
credit.
video too.
On video.
What if we all write it up for next class?
We won't have a class period.
Okay, so those are your main tools on linear independence, this list of equivalent conditions.
Sorry.
To actually figure out whether or not a given set of vectors is linearly independent, you kind of just have to work it out, right? Let me actually take, let me just take a minute or two here to prove that the monomials, let me go ahead and prove for you that these monomials are linearly independent. You should still have time to do the interesting thing. Okay, so claim 1x, x squared, x cubed, x to the n, and this is linear independent subset of polynomials. Polynomials. Okay, so let's see here. Consider c1 times 1 plus c2 times x plus c3 times x squared plus plus cn times xn equals to 0, right? So I intend to use criteria 2. I intend to use criteria 2 to test the linear independence of this set. What's my goal?
C1 equals C2, all of them equal to 0.
Exactly, I want to show all the coefficients are 0. So, starting point, now, to say that this is equal to 0 means that this is true for what? For all x in the reals, actually. If you want me to be technical, that's a function equation. That's an equation of functions, it's not just a, what?
N plus 1, n for the last thing. Because the thing is C3, X2.
N minus 1. Or you can start with 0.
Yeah, I think that's it.
Or I can start 0. Okay, yeah.
Yeah, I'll start with 0.
Sorry.
No, you're right.
You're
It's
assigning this to space.
Oh.
Always start with 0.
I would start with 0.
Yeah.
Okay, so since we're starting with 0, let's plug in 0. If this holds for all x, it certainly holds for 0. So set x equal to 0, what happens?
Did you get 1 equals 0?
I did not get 1 equals 0. I get C0 times 1 equals to 0, which tells me that C sub 0 is equal to 0. Well, 1 down, n to go, right? So
N minus 1 to go.
there's this other thing we learned back when you were younger, in simpler times. You learned that you can differentiate, right? So differentiate. And does it make sense to differentiate? Well, yeah, I know that, let's say differentiate star. Let's call this thing up here star. Can I differentiate that star equation? Yes, I can. That's a polynomial equation which holds for all x. Certainly I can differentiate it, yes. So differentiating it gives me what? It gives me, well, the C0 term goes away, it's constant, right? And you're left with C1 plus 2C2 x plus da 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 plus n c to the n next to the n minus 1 equals to 0. Let me call that star prime. Right? Set x equals to 0 and star prime to obtain what?
C1.
Yeah, C1 equals to 0.
So all the C equals 0.
I hope so. That's what we need in order to make 2 go. For 2 to be true, I need to show that an arbitrary linear combination of these monomials implies that the coefficients of the linear combination are all 0.
So what we now have to do in case n plus 1.
So continuing, so I'm going to do engineer's induction here. Continuing, we find C2 equals to 0 from star prime prime with x equal to 0, right? Until you eventually reach what? Eventually you get to n times n minus 1, all the way down to 3 times 2 times 1, cn x to the, well, times 1, right? If I differentiate c to x to the n fold times, I generated n factorial, right? The coefficient rises along. Everything else is gone to 0 because we're evaluating at 0. We get that is equal to 0, which of course then tells us cn is equal to 0. Right. Now, some would argue that this is not a careful proof. Yeah.
Could you have used induction?
Right. To make this careful, we should use induction. And again, if somebody would like to write the inductive proof on the board before class next time, I'd be happy. If you don't, I will. All right. This brings us to our definition, our penultimate definition for today. And that is definition of a basis. And hand in hand with that is the definition of coordinates. Okay, so think about what I've been talking about today, you see where I was going with this. I was talking about spanning sets, and I was talking about linearly independent sets. And we've come to an understanding, thanks to Dr. Professor Landon's question, that if you want to equate coefficients, you really want linear independence, otherwise there's an ambiguity there, right? So the basis is exactly that. The basis gives you just what you need to be unambiguous about equating coefficients. And that, in turn, will allow us to carefully define the notion of a coordinate map. Let me do it. So let beta be a subset of V. I mean, you can get rid of the equality here if you want or not, folks. It's up to you. I usually leave the equality just for the sake of possibilities, but that may not even really be a possibility. But anyway, beta subset of V, a set for which two things hold. One, it's a generating set. So the span of beta is equal to V. Two, all right, two, beta is linearly independent. If you have these two things, then beta forms a basis for V. Now, there is a small order of business that we need to make clear. Actually, this is not quite it. Not quite it. There's a little caveat, which is actually kind of important. It is missing an N for grammar, and it's an ordered set. What that means is that the order in which the vector appears is part of the structure. So that will matter because otherwise you would introduce ambiguities in the coordinate map that we're about to define. Okay. That forms a basis for V. And I'm going to be greedy here. Partly the reason I'm being greedy is because I want you guys to be able to try to work the homework. All right. I'm going to unravel some of these things I'm saying and prove them in the classes to come. But for now, let me just put it all out there for you. We define, so from a pure logical perspective, this is a little bit out of order. We define coordinate for V, an element of V, with respect to beta equal to, say, V1, V2, Vn, as follows. So the coordinates of V with respect to the beta basis are equal to x1, x2, xn, if and only if, all right, V is equal to x1, v1 plus x2, v2 plus plus xn, vn. So this is called the coordinate vector. Of V with respect to the basis, with respect to beta. Now, the proof that this coordinate vector is defined unambiguously essentially rests on the equating coefficients property, right? Like, if you had two different sets of coordinates for a given vector, that would imply that that would violate the equating coefficients property. That's going to be the proof that that coordinate mapping is well defined. And I'll probably come back to that next time. I want to actually show you an example. So let's let beta equal to, E1, E1 plus E2, E1 plus E2 plus E3. And so these guys is a subset of R3, let's say, keep it simple. Consider the vector V equals to my favorite vector, 1, 2, 3. So let's find the coordinates of that with respect to the beta basis. Reasonably simple example to start with. So what do you gotta do? You gotta try to find coefficients. So what am I trying to find? I'm trying to find, let's just be clear. I'm gonna let v beta equals x1, x2, x3. I'm looking for x1, x2, x3. Need what do I need? I need 1, 2, 3 equal to x1 times e1 plus x2 times e1 plus e2 plus x3 times e1 plus e2 plus e3. I have to solve that equation in order to find the coordinates in our current way of thinking. Let me be more explicit. What is this actually? So this is x1, 0, 0, right? What's this one? This is x2, comma x2, comma 0. And this one is x3, comma x3, comma x3, because e1 is 1, 0, 0. e1 plus e2 is 1, 1, 0. e1 plus e2 plus e3 is 1, 1, 1. Right? Standard basis. Same standard basis we were working with earlier in this course. Now, what do you got here? You got 1, 2, 3. See, so I got x1 plus x2 plus x3, comma, x2 plus x3, comma, x3. I think we can solve this without any kind of fancy solution techniques, right? Just choose your battles first, right? Pick the weakest guy. Kill him. That's actually not a good strategy.
I thought you normally kill the strongest guy first.
That's true. If faced with a superior force, you should go crazy on the strongest guy, gouge out his eyes, and so forth and so on. Not my opinion. This is from G. Gordon Liddy, who had a radio show that was fun listening to. But anyway, yes. The weakest one would be x3, yes. You are the weakest link. Goodbye. All right, so x3 is in fact equal to 3. Sorry, I used green. You can forgive me. Then, if I know that, the next one to pick on is the middle. So I've got x2 plus x3, which is equal to 2, but x3 was 3. So that tells me pretty quickly that x2 is equal to minus 1. Right? And then, let's see here. Almost got it. Then this guy, purple, that gives me x1 plus x2 plus x3, which is equal to like what? x1 minus 1 plus 3 equals to 1, which tells me x1 is actually equal to minus 1 again? Mm-hmm. Okay. So therefore, coordinate vector of 1, 2, 3 in the beta basis is in fact equal to minus 1, 3.
You should put that on the test.
I will put something similar to this on the test. Yeah. Now, by the time we get to the test, I don't know, does it ever get easier to do this problem than we just did it? I don't know, we will eventually see through this problem with greater elegance, but for now it's, yeah.
I liked this problem.
So, so standard basis. Now I use that terminology with meaning. I've been using it all along, standard basis, right?
What's the difference between basis and bases? Because you wrote a
Singular versus plural.
Okay.
I mean, I'm talking about more than one. Is my point. So here, I'm just going to list them for you. Rn is the span of E1, E2, da-da-da, En. This, folks, is the standard basis of Rn. And so I was always using that term, but now it has meaning. I'm saying that's a linearly independent set which spans Rn.
And it would make
And it's a standard one because it's the standard.
a linear combination would basically make a mathematical.
Using anything else as a basis for Rn is weird. Like this would be a non-standard basis for R3. Rm by n is the span of the set Eij such that, let's see here, 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n if I did it right. So that's the standard basis for n by n matrices. This is the standard basis of matrix. Well, you could say, I guess I basically call them unit matrices. Careful with that language. Technically, these aren't units in the sense of group theory. They don't have multiplicative inverses. Most of it is 0, but certainly not multiplicative inverses, not existing for these guys, right? For example, if I have A, B, C, D, I can write that as A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1. I feel like this was a homework problem. It's almost like I planned for this moment. This shows you, in fact, this is, of course, E11, E12, E21, E22. This shows you that any 2 by 2 matrix is the span formed by the span of these 3 basic matrices. They're clearly linearly independent. You can prove it. So, for example, what's the coordinate vector then? So if I let beta equal to E11, E12, E21, E22, right? And if I call this thing A, big A, what's the, is it actually seeing what I'm writing right now?
Yeah, but don't go.
Don't go lower.
Yeah.
Then how about up here? Coordinate vector of A with respect to the beta basis would be equal to the coefficients of the linear combination, right? A, B, C, D. That would be the coordinate vector of this matrix A. So finding coordinates is as simple as is finding how a given vector is obtained as a linear combination of the given vectors in the basis, and then you pick off the coefficients. The fascinating thing, the useful thing about coordinate vectors is that they are column vectors. I know my notation looks like row, but it's column, right? They're column vectors, which means we know all that stuff from the first part of the course about them. You know, we're thinking about sets of them and so forth. What if let me just, I said as an ordered basis, I really haven't made good on that. One last comment for today, and then just so you appreciate why the order matters. If we chose another basis here for this example, say gamma was equal to E22, E11, E12, E21, if that was the basis, and I asked what's the coordinate vector of A with respect to the gamma basis, it's not the same coordinate vector anymore. You see, the order matters. E22 was the D1. E11 was A. E12 was C. And E21,
That used to be easy.
oh, is that right? Oh, E21 is C, I'm sorry. E12 is what? Is D. C, yeah. So of course the coordinates of a given vector will be different when you look at it from different basis perspectives. the problem of studying how they're related is the problem of coordinate change, which is probably the hardest problem that we look at all semester. Problem of coordinate change is solved. And that's it. Thanks, guys. Have a good weekend.